half-past by my clock. So let me then introduce Ray Osborne, and he's going to tell us a bit about why NeXus is so great. So over to you, Ray.
Thank you. Okay, so can you all hear me? Yeah. So yeah, thank you for the invitation. As I think Thomas and Bridget knew before they invited me, I am not here because of my expertise in reflectometry. I'm not sure if I've ever actually done a reflectometry experiment. Although Suzanne Veldhuis is a colleague in the neutron X-ray scattering group with me, and until he retired, so was John Felcher. So I may have learned a little bit by osmosis. But the reason I'm here, I think, is because I've been involved in the NeXus data format pretty well since its inception in the early 90s. Let me preface my remarks by saying that although I am a member of the NeXus International Advisory Committee, who I'll introduce in a minute, I'm talking entirely in my own capacity. All the opinions I express will be my own. I'm not really an official representative in that sense. However, I hope that this is useful to your deliberations. I heard Joachim Stein this morning, and it made me quite nostalgic for some of the discussions that we had in the early days of NeXus. So let me kick away. Let's see if I can get this to work. Okay, why NeXus? So firstly, let me just give a brief overview of the status of NeXus. So there's an old joke, that the great thing about standards is that there are so many to choose from. In the case of NeXus, actually, that may not be true. There really is, I think, only one well-established standard, at least an international standard, for the storage of data at neutron, synchrotron, X-ray facilities. There are, of course, standards for subsets of instruments or techniques, but this is the only one that's widely available. And is over the last few years, it's become the official archive format for instance, the entire instrument suite of a number of facilities. This is mostly at neutron sources because synchrotron X-ray sources tend to devolve responsibility for these decisions down to the beamlines. But places like the SNS and ISIS, and I believe still policy in the future, the ESS, will store the data as NeXus files. And there is active participation in the NeXus International Advisory Committee from nearly 20 facilities in Asia, Europe, and North America. So this is a very active community. We have official meetings where the whole committee convenes once every 2 years or so. The last one was, of course, virtual. But we also have code camps where we discuss particular technical issues pretty well every year. And there are monthly online meetings, which have been going for a few years now to deal with maintenance issues. And there are some, I think, if there's anybody here from Diamond, you can correct me, but I believe that the Diamond was requiring detector manufacturers to support NeXus as an export format. Certainly Dectris has actually worked with the committee over a number of years to make changes to the format specifically for their needs with the Eiger and I guess is it Jungfrau, the next series of detectors that they're developing. So that's actually an important stage in the development of any, showing a certain level of maturity. So here's just a map of the facilities that are involved in the NeXus format. From the west, they go from the Advanced Light Source in California all the way to J-Park Pulse Neutron Source in Japan. North to south, there's a Canada Light Source in, is it Saskatchewan, I think, all the way down to the Bragg Institute in outside Sydney. So geographically, it's very diverse. There are quite a few facilities in Europe that are represented. For some reason or other, actually, the European Spallation Source is not currently represented, although Tobias Richter was the chair of the committee, so I presume that's just some temporary thing. But anyway, so as I say, it's fairly well established. So let me give a very brief description. I don't know how many people here are actually completely familiar with NeXus, so I apologize if you already know all this stuff. But basically, NeXus files are HDF5 files. But if you just open an HDF5 file, there's nothing to tell you what's in it from the HDF5 point of view. So NeXus adds some semantics. These are simple design rules to make the files easy to navigate, and a list of definitions that cover most experimental metadata. So the purpose of these rules is to try and make them self-describing as much as possible. And I hope to show at the end, if I have time, that it's possible to open NeXus files from a variety of sources and get a pretty good idea of what's in them, without having any documentation whatsoever. It uses the hierarchical design in a similar way to a file system, and the advantage of the hierarchy is that you can store non-essential metadata, sort of obscure sample environment logs and things like that down. You can bury those at a low level of the hierarchy, while when somebody opens a file, they immediately see what's really important to them. For instance, the data that they want to analyze. And then I'll describe it a little bit later that an important part of the standard is that there are base classes which effectively define a glossary of terms. So, if a lot of people have decided that a particular type of metadata is important, then we agree on how it's going to be named and what group it should go into. Okay. So actually, this is a sort of a schematic of what a typical NeXus file might look like. There are three types of objects, just as there are in HDF5. There are groups, fields, and attributes. And so groups are in a file system, a bit like the folders or directories in the file system. Fields are like the files themselves, and attributes are extra metadata. Now, unlike HDF5, we actually add classes to these groups to define what's in them. Okay, so for instance, the top level of any NeXus file always consists of an NX-entry class. This is meant to encapsulate everything that constitutes a measurement in however you want to define it. So I don't know, I suppose if you're doing reflectometry with spin flip and non-spin flip, you would put those in the same NX entry, but if you then change temperature, you put that in a different one. And within that NX entry, you then store information that is relevant to the measurement, such as information about the sample, for example, its temperature. The instrument itself, the NX instrument group will actually usually contain quite a few other groups, which might define the detectors or the choppers or the apertures or whatever in a fairly logical system. And then the most important in many ways is the data groups, which are normally there at the top level. They have a class of NX data, and they encapsulate the information which is basically the result of the experiment. This is what you want to analyze. And it's designed in such a way that the data, which is typically some kind of multidimensional array, has associated one-dimensional axes. So you can, if you have a GUI, you can just double click on that directory and immediately get a plot, which has the suitable annotations, suitable units, is readily understandable. And I hope to give examples of that later as well. So all the NeXus files look roughly like this. I mentioned that there were base classes, and so over the years, the NeXus committee has defined a whole set of these base classes to define what are effectively objects in an instrument, on the beamline. Apertures, attenuators, choppers I mentioned, so if you have one of these in your beamline, you would put a group in there, and if you then look inside the base class definitions, there are suggested names for things like rotation speed, pair separation, whatever that means, etc., etc. These are all defined on the web, and basically they're naming conventions. They want people to call, we want everybody who's going to measure temperature to call it temperature rather than temp or T or whatever, so that, and of course there is some degree of documentation here so that we know what people mean, by each object. But there are also, and this may be of particular interest to there are application definitions. These used to be called instrument definitions, but then we realized that actually it's more important that what you have is a definition that applies to a particular type of application that is going to analyze your data. So they describe out of those base classes what items are actually necessary, what is the minimum number, what are the essential things, what are the optional things, what are the metadata that you really need in order to analyze data of this type. Okay, the minimum required information. And so you can see that there are quite a few here that might be relevant to this group. There's an NX scan, which is for a monochromatic reflectometer, and there's NX RefTOF, which is the application definition for data from a time-of-flight reflectometer. And actually, I think I can show some of that a little bit later. Now, I have no idea of the provenance of these applications. They may not do what you need. If they don't, then I would certainly encourage your organization to get in touch with the NeXus committee. In fact, I didn't say it earlier, but in fact, I think it might be appropriate for also to have assign a member to the NeXus International Advisory Committee to, act as an interface to this organization. We tend to have good facility representation. We don't have such good representation from user communities because they're not as well organized as you are. Anyway, so just as an example, I mean, Suzanne, I know, uses GenX sometimes. I know nothing about it. But supposing you wanted to use GenX to analyze your software, what you would want is for the facilities to export the data in a format that GenX could read so that it had all the information it needed in order to complete whatever analysis it does. Now, this interface has been, the idea behind this sort of interface has been around for a while. I think it's not as well developed as it could be. And that's really a sociological question. And I'm sure you're finding this when you're setting up also that part of this is just getting agreements from user community or from the facilities. And sometimes that's much harder than the technical aspect of defining a standard. So anyway, so if this is of interest to you, or if you're a developer of GenX, I don't know if there are anybody at this meeting, then, I think it would be useful for an organization like also to essentially come up with some kind of application definitions that would make it easy for the user to use whatever application they want to provide. Now, this actually gets me back to, I wanted to go a little bit back into history of NeXus, partly because when you're older, you like to reminisce, but it's also partly because it actually, there is a sense in which NeXus has been extremely successful, but it hasn't succeeded in the specific goals that I think it was originally set out to accomplish. And in particular, it's got very good buy-in from facilities, but I suspect that it's not nearly so well known by the user communities themselves. If I were in the same room as you, I'd probably be asking you to put up your hands if you've ever actually, opened a NeXus file by your own application or not. And I suspect the number might be quite few. And that's sort of a little bit ironic because when NeXus was first set up, we had a series of meetings, a couple that are gone, 94 and 96, and one in 95, when I think the NeXus name was finally adopted in Gaithersburg. Oops, sorry, I didn't mean to do that actually. Where the original goals of NeXus were laid out, and it was thought of as being a data exchange format. It was not meant to be an archive format for the facilities. It was actually meant for the itinerant scientific user, somebody who uses machines all over the world, and even uses neutrons and X-rays or whatever. And the idea was to empower people to essentially do their own kind of analysis that they want, rather than be constrained by whatever analysis the facility provided. Okay. So if you're a GenX lover, then you can use GenX, from anywhere. I know that actually GenX has lots of imports, and as I say, the nice thing about standards is there's so many to choose from. But this would considerably simplify things because you can store much more complex information in NeXus files. Anyway, so that was the original idea. In fact, if we had the very first meeting, we had a working group on data exchange formats, and here were some of the statements, and I suspect they're reflected in the kinds of discussions that you have been having in also. So an implementation of a data exchange standard would make it possible to use your favorite program in a transparent manner without having to worry about idiosyncrasies of local data file formats. You'd only need a single conversion routine at each instrument rather than a multitude of such routines. And it would facilitate the use of same software packages at multiple sites. So in other words, it was meant to give the users the option to do what they wanted rather than to be constrained by the facility. And I think to some extent, I think we've lost a bit of sight of that. I mean, the problem, of course, is partly that, for instance, particularly neutron instrumentation has become so complex that if you're going to do an experiment at the SNS, you have to use an established framework like Mantid, because there are so many different types of corrections you need to make, particularly converting from event mode to histograms, before you can even look at the data. So there are reasons behind this, But I think it's true that that on the whole, people go to the SNS tend to analyze their data, within Manted at the SNS rather than to take their data home and use their own software. But this community perhaps has other ideas. Now, one of the reasons this hasn't happened so much is I think 20 years ago, we would have required the scientists to be writing in C or C++, because we weren't allowed to program in Fortran in those days. Now Python has actually become popular among scientists, and I think this is an opportunity for us to revive the empowered scientific user, because it provides an intuitive language to process data, and which encourages, I think, experimentation, etc. And it gives you the kind of flexibility that you need to be able to cope with data from multiple sources. And I'll hopefully give some example of that. So NeXus actually started by constructing a C API for reading and writing these files, because it was actually written originally for HDF4 files, which were really complicated to write. This has now become a bit deprecated because HDF5, now there are only ever HDF5 files, but HDF5 keeps on introducing new features which are difficult to keep up with, swimmer mode and virtual data sets and all sorts of things like that. And so the committee decided they didn't have the bandwidth to keep up with that. However, Python, that's a slightly different story because it's built on H5Py, which does keep up with all these things and actually provides an interface that means you don't need to know about some of these low-level details. But it provides on top of H5Py a very intuitive syntax, I believe, anyway. So, for instance, that example I showed earlier, here's just how you would write that whole data tree just in a set of 5 lines or something. And what's more, it does a lot of the little tweaking to ensure that, for instance, if you double click on the data, it will produce a sensible plot, defines axes and signals and things like that using various attributes. And of course, you can read entire data trees, entire files, just in a single line, and then you have access to everything in that very conveniently. So the Python API is, as I say, is very concise, and it actually, so if you're an H5Py lover, and I commend you for it, it's a brilliant program, but on the other hand, because NeXus has added some extra semantic sugar on top of HDF5, it can be quite cumbersome to reproduce in using H5Py all you need to make the file completely standard compliant, whereas the NeXus format Python API does that for you. Now, this is a bit of this is a kind of shameless plug. This isn't really the subject of my talk, but NextPy is a GUI we've been developing for about 10 years at Argonne, and we use it all the time. But it is an example of, I think it provides some useful examples of how having a common format like NeXus actually frees you up to have fairly generic applications which will give you all the power of the NeXus files very conveniently. And so the idea of, so I think it's so, if you want to go and use it, I'll show you how you can download it. That'd be great. But I think anyway, it just shows you what are the advantages of using NeXus rather than some other kind of format that you might want to develop yourself. And it's designed to be a kind of a simple toolbox for users who have already probably reduced their data using Manted or Dials or whatever is used in your facility. It's not designed to replace these frameworks, because sometimes there's some, as I say, there's some very complicated event mode processing that has to go on, etc. But once you've got the data in some kind of histogram form, then certainly in my experience, Manted has a fairly steep learning curve. And the result is that the users tend to become dependent on the instrument scientists to do the analysis for them rather than to become completely independent. And so the idea of NextPy is we want the facilities to export the data in a convenient form, and then we can play with the data the way we want to. It's visualizing the data, it's comparing data, and it's developing new algorithms. So this is just a quick slide showing how you'd install NextPy, and I think these slides will be made available later. So if you do just want to note something down, that top URL is all you need. There's some fairly decent documentation. But anyway, it's available on Conda and the PyPy servers. And it's a very simple program. Basically, it's just bolting together some very popular Python packages. There's a PyQt tree where you load the NeXus data. There's a matplotlib window, and there's an IPython shell. And they're all linked together. So you can plot from the IPython shell, or you can manipulate data in the tree also from the shell, et cetera, et cetera. Now, and various other things. And the advantage is that it means you can open files and look inside them and do some fairly simple things like plotting the data just by double clicks. You can even cut and paste data from one file to another and things like that. And it contains a number of things for instance, for giving you convenient access to special matplotlib features like skewed axes or symmetric color plots or reordering legends, things that you might have to spend a lot of time in the documentation reading. Now, but this is perhaps the key thing that we found on NextPy has been the biggest influence on how our group has worked. And that is just a simple script editor. It's nothing fancy. It's just, it happens to be colorized, but it's just a text box. But when you hit run script, it runs it in the shell. And this has transformed the way our students and postdocs have learned how to manipulate data. They actually have developed their own routines using this as just a simple sandbox to play around in. And actually whole new methods of data analysis have been pioneered by our postdocs, even though they're not experienced programmers. Like, I don't know if you're familiar with 3D Delta PDF, that's something we've been working on. But Matt Krogstad actually developed all that within just a simple script editor. So it's an example that if the language is convenient, then you can hand it over to students and postdocs who are not programmers, and you can get really powerful results. So I think, in fact, let me, oh yeah, well, okay, well, very quickly, you can extend NextPy if you want to, because you can add extra menus as a plugin architecture if you wanted to build your own applications. Let me quickly, I want to leave some time for questions, but let me quickly show an example of NextPy. And this isn't to demonstrate NextPy so much, this is to demonstrate the advantages of the NeXus format. So hopefully you can see, you can all still see the NextPy window, can you, which is here?
Yeah, it looks good.
So, so I've loaded one file already. This is actually some old IPNS data. Somebody was worried about data that might be 30 years old. It is nearly 30 years old and it's still accessible. But anyway, but when you open the hierarchy here, there's a top level Linux Sentry group. There are monitors, and the instrument group contains information about the detector, about the monocomator. And I think it's fair to say that anybody looking at this could pretty well work out what's going on with this file, even if they knew nothing about, in this case, time of flight chopper spectrometry. In particular, you can double click on the data group and you get a plot. And then you can take various cuts and projections and things like that. And this is the basics for NeXus, is that, you know, without knowing anything about the data, you can immediately go and find what is the relevant stuff. Actually, there's very important metadata. There are monitors. There's monitor 1, there's monitor 2, and you know, if you wanted to do some kind of data analysis, you know, the fitting routines that allow you to fit the data and plot the model, and then you can see, well, we plotted a, you know, we fit a Gaussian to the peak. So it's easy to navigate. It's easy to find the various information you need, and everything that's in this is available from the command line. So if I just type, you know, I want to know what the temperature was, then you know, there it is. It's 8 Kelvin, and in principle, I could actually change it here if I unlock the file. Okay. But the thing about this is then that you can load data from any kind of format. This is actually Zane's data from ESRF. I know nothing about Zane's, but this is stuff that was used to, well, so here, anyway, here is Zane's data. I was able to plot the data straight away, again, without knowing anything about Zane's. There's not too much metadata in this instrument. There is some, I guess, in here. Actually, probably more than you want to know. But supposing I want to look at CNCS data from the spallation neutron source, this is inelastic neutron scattering data. Again, well, in this case, this is process data. So actually, there is not the complicated file, but here is some inelastic neutron scattering data, and I can choose to start scrolling through this. Actually, let me put this down. And if you know anything about inelastic neutron scattering, as you can change the energy in the Z tab. So this is 4-dimensional data set actually, and you can start seeing phonons dispersing away from the Bragg peaks. Okay. One last example perhaps, which is this is some Corelli data we collected actually only a few weeks ago. Now this is an output from Mantid. It has a standard MD histo workspace. They're not always standard compliant. I'm showing you some examples of that, but here's some diffuse scattering data from strontium chloride if you're interested. So now you're interested, of course, in reflectometry data. So Suzanne pointed me towards some reflectometry data that which I think actually looked as if it's the same kind of thing that Tim was showing earlier. Here's a bank. Now, unfortunately, Mantid doesn't always produce standard compliant files. So if I double click that, it says the defined axes are not compatible with the signal. But I can still plot the data itself. And now there's not, oops, I didn't mean to do it. There's not very much there. So I'm going to change the axes and then do an integral, find out where the interesting data is. If I go to axis there, I'm going to do a, I'm going to go lots of times of flight. I'm just going to plot it against time of flight and see what is the integral of this stuff. And it seems for some reason this peaks at around 30,000 microseconds, I presume. So if I go to the 30,000 microseconds in the z-axis, then indeed, presumably this is the specular reflection in the peak, and then I can, if I wanted to, I could plot this against axis 0. Let me see, surface, and then and plot a one-dimensional data set, and and I'll fit pseudo voids because that seems to be what it looked like. On either model, I'll fit it, and I'll plot the model. So the point is, I've now turned up what is the center of the specular peak. The reason I'm doing all this is just to show that I know nothing about reflectometry. I actually knew nothing about the contents of this file, but I was able to actually go through that and actually, I think, extract some useful data. And of course, if I did know what was in the file, then it would be even more useful and more helpful to all of you. Oh, actually, I should stop now. So this is. I was going to say that one of the advantages of NeXus is you can store a huge amount of information, such as things like powder calibrations, within the file, and as well as the data itself. And this is one of the advantages. Sorry, it's not in there. This is one of the advantages of having a sort of a generic format. Okay, so let me. Where you can just drop things into the file. Okay, so demos always take longer than it should, and I should stop now. So let me quickly go back to my talk and just put up a summary slide. I think an organization like also it's very timely actually for the NeXus format, and I think if you were to interface with the NeXus International Advisory Committee, you could produce, you could help us to make the data format or the application definitions that you need much more relevant to the programs that you want to run. But then you can pass the data on to the users, knowing that there are convenient APIs, for example, in Python, which allow you to access the data after they've been produced. And I wish I had more time to show you examples of that, but I've already used it all up. So I'm happy to take questions if you think there are time, and thank you for your attention.